anyway, however, that's kind of going right up to 104 is kind of skipping over a few steps. I thought it was good to start with a few simple machine learning projects just to see what they can do. So let's take a look at ML100, and we're going to use Google Colab. So I launched Colab, and then I make a new notebook, and let's see. Oh, good. This is what I wanted. Okay. Earlier today, I ended up with a notebook all full of extra ads or something in it, but apparently that was my mistake. All right, so here, we're just going to import TensorFlow and make sure you've got it. TensorFlow is the library. It's one of several machine learning libraries, and it's the first one we're going to use here. So you put in the code and run it, and it should print out a version number. There we go. Okay, version 2.12. All right, so we can get it. And it has a version number. So if you have a relationship between two parameters, x and y, you can start with a relationship here where you can see when x goes up by 1, y goes up by 2. So a human can look at these patterns and pretty quickly figure out that y is 2 times x minus 1. And that is the process we'd like the machine to do the learning of. Instead of a human having to program in this equation, the machine is going to find that relationship and fit it. So this is the code that will do it. And that's why I thought this class would be worth teaching, because it's not very difficult. You don't need to write a lot of code. You import this TensorFlow library, then you define the x and y values, here they are, and then you just call model fit. Having chosen a model, this is a neural net with one neuron. So it just can fit a straight line, and then to test it, we're going to predict the value for 10. Now we know y is 2x minus 1, so the right answer for 10 is 19. And we can tell how close it is by how close the answer is to 19. So it's doing 500 steps of training, and when it's done, it predicts very close to 19, 18.9. All right. And this is using a standard gradient descent algorithm. So what it does is it just guesses some values of the parameters, and then it moves them in a way to lower the loss. And you see here's the loss. The loss is a measure of the error, probably root mean square. And see, it started at 61, went down to 48, 38, and so on. So it started being very wrong, but after a while it got very good, and the loss got down to 10 to the minus 4, which is very close to 0. So that makes sense because we're giving it straight lines. So this is a simple single neural net here. X goes in, y equals mx plus c. And so the two parameters are 2 and minus 1. The slope is 2, the intercept is minus 1. That's the right answer. All right. And so we can see what it learned. We can run it again and print out the weights. The weights are those parameters, the slope and the intercept. So I can do this, just run it again, and at the end, instead of just printing the prediction for 10, I'm just going to print the weights. So there we are. Here's 18.9, and what it learned was 1.997 and minus 0.99, when the right answer is 2 and minus 1, so it got very close. It got within 1%. So it's easy enough to do that. So a straight line neural net can fit straight line data. So the next thing is, what if there was noise in the data? So let's change the y values to these values. Let me get back to the code up here. All right. And so I'm going to put in that stuff instead, and I guess I'll comment out the first one. So I just added a little bit of random variation to the y. And now when I run this one, it starts with a loss of like 0.4, and it goes down to 0.000, and it doesn't get down to 10 to the minus 4 anymore. It can't fit so perfectly because there's noise, but still, it's pretty good. 18.9 is the prediction, and the parameters are 1.99 and minus 0.99, so it's able to tolerate some random noise and still fit a line through it pretty well. Now, if I give it something that's not a straight line at all, x squared minus 4x minus 5, then I'd be having these values for y. And the model assumes a straight line. It only has one neuron with only two parameters, slope and intercept. So logically, it's probably not going to be very good at fitting data that really isn't a straight line. I'll comment out the old stuff. All right. So let's run this one. And so the loss is like 5 and 4, and it looks like it's not going to get much below 4, which is like 100 times more loss than before. And so now it's just got minus 0.72 and minus 0.5, minus 5, ridiculous numbers, and it's not fitting the data very well at all. So as you'd expect, a straight line is just not going to fit through that curve very well. So let's make a model that can actually fit a curve. And that takes a few more lines of code. That's here. Let's just have a new block of code. All right, and here we're going to use a lot more neurons. Instead of one neuron to convert X to Y, we're going to have one neuron to take X, then a layer of 64 hidden neurons, and another layer of 64 hidden neurons, and then one layer of output. So there's a lot more processing in the middle, and it can do things far more complicated than just a straight line. And what we're going to use is 0.1 times X times cosine X plus some randomness. So it's going to be a curvy, wavy thing. And then we're going to plot out the answer so we can see it. So here's the model, and if you look at the top, it tells you this is the first neuron has 2 parameters. The 64 neurons here are 128 parameters, and then the next line has 64 times 64. Each one of these it puts in the others, that's another 4,000 parameters. So the total number of parameters is now 4,000 instead of 2. So it can fit complicated curves, and here we go, slopes, the loss starts at 0.19, and it goes down to 0.01. And there it is. It drew that red curve through the blue dots, and as you can see, it did a pretty good job at fitting this complicated curve. So that's an example. And now, to fit the flag, you can try some variations. Try changing the number of layers, number of units per layer. You can have a variety of different number of parameters and find out which one works best. You will have to run it more than once. For example, if I run this one, notice the final loss got down to 0.01. There's some randomness in the process. If I just run the same thing again, I'll get a different final error. It was 0.01 last time. And this time it's 0.017, which is pretty close to what it had. Anyway, the point is there is randomness in the process. So when you're trying to compare models, you have to run each one of them 3 times to get the average loss at the end. All right, and then there's ones here where you can vary the amount of noise and so on. There's a 0.1 is the amount of noise. You can change it, try various correlations, and see how well it can handle different models and different noise on the input. One thing I was surprised at, I thought you don't need 1,000 points at all to trace out this curve. It seemed to me like 20 points would be enough, but in practice, even 100 points wasn't enough to make a good fit. It really seemed like you needed a lot of those points. And so anyway, that's one to get started where you just get to practice simple curve fitting, which is one of the types, that's the regression process of machine learning. So let me stop this one.